Hi guys, hope you're having a wonderful day so far. We are going to talk about electron configurations and how to get them from the periodic table. So no need to memorize the order because you can get it from the periodic table. So if you remember, we have energy levels first. So we're going to start with those. And the periods on the periodic table represent our energy levels. So if you remember, energy levels were like N, and they go 1, 2, 3, 4, 5, 6, 7, and so on. So this is going to be period number 1. This is 2, 3, 4, 5, 6, and 7. Now there's an infinite number of energy levels, but the elements we've discovered so far in their ground state only occupy up to the 7th energy level. So then we have the sub-level, and the sub-levels are S, P, D, and F. Theoretically, we have more, but based on the elements we've discovered so far, we only have elements that occupy up till the F sublevel. So let's start with S. So S has one orbital, which means it takes up to 2 electrons. So can you find somewhere on the periodic table a column of 2? Well, you can see it right here. Let me do it in blue. So see how this is a block of 2? And so that's our S. And so where we have period number 1, this would be our 1s. This would be 2s, 3s, 4s. I'm going to make my pen a little bit thicker here. There we go, 4s, 5s, 6s, and 7s. So that's my S block. Now you'll notice that we need 2 boxes for the S's, and in the first period here we only have 1 box. Well, there is our other box. This is still considered 1s. Some people argue that helium should really be here, but it is a noble gas, so that's why they put it there. All right, so we got the S. Let's move on to the P. So change the color here. Let's go with red. So the P sublevel has 3 orbitals. And remember, each orbital contains 2 electrons, and so you can fit up to 6 electrons in a P sublevel. And so do you see a block of 6? Right here. There's your P block. So we don't have a 1p, that doesn't really exist. This right here is our second period, and so this would be our 2p. So that block of 6 right there. This would be 3p, and then 4p, and then 5p, and 6p, and then 7p. Okay, we got our P's. Let's move on to the D's. So let's do those in green. So D has 5 orbitals. And so if we have 5 orbitals, we can take up to 10 electrons. So do you see a block of 10? Well, right here, that's your D block. So the D is kind of funky. I call it the wacky one off, because it is 1 off from the count. So what I mean is, if you look right here, this is the 4th period, but this is 1 off from that. So it's not 4D, it is 3D. It is 1 off from our count. So the next one, this is the 5th energy level or 5th period, and so this would be 1 off from that, so 4D. This is the 6th period, so 5D. And this is the 7th period, so 6D. Now you'll notice that this right here is this. So this is my 5D, and this is my 6D. Just that one block here. So lanthanum belongs right here, and then cerium through lutetium belong here, And then here is where actinium belongs, and then thorium starts there. Okay, the last one is F. So F, let's do that in purple. F has 7 orbitals, which means you can hold up to 14 electrons. Well, do you see a block of 14? Well, that's all what's left is right here. There's the F block, and F is even wackier than the D. It is 2 off from the count. So what does that mean? Well, right here, this belongs, we said right there, right? And this is my 6th period. And so that would be 2 off from 6. So that would be 4F. And then right here, this belongs right there where the 7th period is. So 2 off from that, this is 5F. So I want you to be able to label a periodic table like this. So what you do is you start by labeling your period. So you go 1, 2, 3, 4, 5, 6, 7, and those are your energy levels. Then you start with the S. So you look for a block of 2 because S can hold up to 2 electrons. So it's right here. So you go 1s, 2s, 3s, 4s, 5s, and so on. Next is the P. The P holds up to 6 electrons. So you find a block of 6. So right there. And it starts with the 2p, 3p, 4p, 5p, and so on. And then the D would be a block of 10, which would be the transition metals. But remember, they're just 1 off. So if this is the 4th period, you go 3D. 5th period, you go 4D, and so on. And then the F holds up to 14 electrons, and so you find the block of 14, which is the inner transition metals, but they are 2 off from the count. So if you're in the 6th period, you go 4F. If you're in the 7th period, you go 5F. So what do we do with this? Well, if we want an electron configuration, well, guess what? The lowest energy levels and sublevels are listed here for you on the periodic table. So first we have the 1s, and there's 2 of those, then 2s, 2, then 2p, 6, there's 6 of these boxes, then 3s, 2, then 3p, 6, then 4s, 2, then 3d, 10, then 4p, 6, 5s, 2, 4d, 10, 5p, 6, 6s, 2, 5d10, and so on. So you can get the order from the periodic table here. So let's try a few. So let's try fluorine. So what you do is you find the element on your periodic table. Fluorine is right here. And you start from the very beginning of the periodic table and you write down what sublevels you see and how many boxes. So you start with 1s. So I'm going to write 1s. And how many boxes of 1s do we see? We see 1, 2. So 1s, 2. Okay, we're done with the first period. Let's go to the next one. Then you find 2s, and there's 2 boxes, so 2s, 2. Then, after the 2s, 2, you go here, 2p, and then you count how many boxes? 1, 2, 3, 4, 5. So 2p5. For our valence electrons, those are the electrons in the highest energy level. So what's the highest energy level here? Energy level number 2. So we have 2 electrons in the 2s sublevel, 5 electrons in the 2p sublevel, for a total of 7 electrons in that second energy level. And so 7 valence electrons. Let's try zirconium next. Zirconium is right here. So we're going to start from the beginning of the periodic table. So we see 1s, and there's 2 boxes. So 1s, 2. Next we see 2s, and there's 2 boxes. So 2s, 2. Next we see 2p, and there's 6. Then we see 3s, and there's 2 boxes. Then we see 3p, and there's 6 boxes. And then we see 4s, 2. Then there's 3d10. and then 4p6, then 5s2, and then finally 4d1, 2. That's kind of long. How many valence electrons are there? Well, the highest energy level is the 5th energy level right here. And so we have 2 valence electrons. Not because of these right here, but because of those. The 5th energy level is your highest energy level. Okay, let's try a few more. So next is phosphorus. Phosphorus is right here. Now, you saw with the last one that these could kind of get lengthy, and you know, chemists are kind of lazy. They try to come up with shortcuts. So they came up with something called the noble gas shortcut. And the noble gas shortcut is basically you find the noble gas that comes before the element you're interested in. And so if I want phosphorus, then the noble gas that comes before it would be neon. Remember, noble gases are group 18. And so the one that comes before the phosphorus would be neon. So what you do is you write that noble gas in brackets. So you write brackets Ne. What that means is this is a shortcut that means that you have written the electron configuration up to and including neon. So by writing this, that means you've done 1s2, 2s2, 2p6, and you ended at neon. So now all you have to do is just do the rest of the electron configuration after your noble gas. So starting from here all the way to your element. So then we see 3s2, and then we see 3p, and 1, 2, 3. How many valence electrons are there? Well, the 3rd energy level is our highest energy level. So all of these are in the 3rd energy level. 2 in the s, 3 in the p, 5 valence electrons total. Okay, let's try nobelium. So let's try to find where nobelium is. Nobelium is right here. So what noble gas comes before that? Well, the noble gas that comes before that would be krypton, which is right here. So we're going to write krypton in brackets. And then that means that we've written 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 4p6. Sorry, did I mess up? Let me say that again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. That would get us all the way up to krypton. So now all we have to do is do after krypton, so starting from here and going up to nobelium. So we see the 5s, and there's 2 of those. And we see next is 4d, and there are 1, 2, 3 of those. For our valence electrons, the highest energy level is the 5th energy level. And so there are 2 valence electrons right here. Okay, let's do the next one. Let's do krypton. So krypton is right here. Well, krypton is a noble gas, but we can't just write krypton. I mean, that's not really writing the electron configuration, right? So we got to go with the one before it. So the noble gas that comes before krypton is argon right here. And so we're going to write argon in brackets, and that will take us all the way up to 3p6. So argon, and then what we would have left after argon would be right here. So 4s2. Then we have 3d10. And then finally we have 4p6. How many valence electrons? Well, the 4th energy level is our highest energy level. So 2 and 6 is 8 valence electrons. Okay, let's do the next one. So the next one is iridium. Can you guys find iridium? It is a transition metal. Do you see it right here? So what noble gas comes before that? Well, xenon comes before iridium, so we're going to write xenon in brackets. And then we're going to start after xenon. So right here we have 6s2. Then we have 5d. And right here you see, right there, you have 5d. You see one box, 5d1. Then you move on, and then you have 4f14. And then you go back, right? When this ends, you go back here, and then you have 1, 2, 3, 4, 5, 6 more boxes that are in the 5d. So it is acceptable to write it this way. This is totally fine. However, since we have 5d1 here, like a 5d box, and then 6 more 5d boxes, we can combine these to make them 5d7. So another way to write this would be xenon. Then you would write 6s2, 4f14, and then 5d7. You can combine those d electrons. Okay, let's go with astatine next. Astatine is the rarest element that we have on the periodic table. And it is right here. So the noble gas that comes before that is xenon again. And then after xenon, I see 6s2. And then I see after that 5d1, then 4f14, and then I go back and 5d9 again. So if you want to write it that way, you can. I know that I'm going to finish all my f's and all my d's, so I'm just going to write it all as the d's as 1. So I'm going to write 4f14 and 5d10. If you prefer, you can write it as 6s2, 5d1, 4f14, 5d9. That is totally fine. It is more traditional that you would combine them, but if you don't want to, that is totally fine. Then we go to 6p, and how many boxes do we need to get to astatine? So 1, 2, 3, 4, 5 boxes, so 6p5. We forgot to do the valence electrons, so 6th energy level here is the highest, so 2 and 5, that is 7 valence electrons. I forgot to do the ones for the iridium here, so for the iridium, highest energy level is the 6th energy level, so there are 2 valence electrons. Okay, californium is next. Let's pick a different color. Let's go with this one. Californium is an inner transition metal. It's right there. So let's see, where does this belong? This belongs right there, and so the noble gas that comes before it would be radon. Radon is right here. So we're going to write radon. And then what comes after that would be 7s2. And then after the 7s2, so we go here, we find a 6d1. And then we see 5f, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5f9. My valence electrons, my highest energy level is the 7th energy level. There are 2 valence electrons. So I want you to notice something with the transition and the inner transition metals here. You'll notice that when we have transition metals or inner transition metals, we always have 2 valence electrons. So if you have something that ends with S1, then that's going to be 1 valence electron. If you have something that ends with S2, it's going to be 2 valence electrons. If you have something that ends with D's or F's, it's still going to be 2 valence electrons. And the reason is that your D's are 1 lower in the count and the Fs are 2 lower than the count. Remember, we call them wacky 1 off and wacky 2 off. So let's say, let's go back to nobelium right here. See how it's 5s, but then 4d, because the d's are lower. So the s energy level is always going to be higher, and so the s electrons are going to be the valence electrons. Let's look at californium. So see how the s's are higher in energy level than the d's and the f's, and so the s's are always going to be your valence electrons, and so there's going to be 2 valence electrons. Excuse me. So if you have a transition metal or an intertransition metal, your S's will still be higher in energy level, and so the S's are going to be your valence electrons. When you get to these here, where it's P1, the S and the P sublevels are in the same energy level, so those all count. So this would be 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. Let's write that down. So 1 valence electron for this group, 2 valence electrons. All of these are 2 valence electrons. For the most part, we're going to talk about some exceptions in a minute. This would be 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons. These are all 8 valence electrons. And this one is just 2 valence electrons. Remember, because helium just has 2 electrons total. All right. The last topic here is the chromium and the copper families exceptions. So these electron configurations, the rules for them are man-made, right? We watch or we observe the electrons fill up these orbitals, and we try to come up with a system that fits nature, how electrons actually fill up these orbitals. There are always exceptions though, and so we're only looking at a few of the exceptions, not all of them, but the chromium family and the copper family seem to show an exception. So let's talk about that exception. Let me do it in orange to match. So let's say I want to do chromium, the electron configuration for chromium. So this is how we would normally do it. Based on what we learned. So we would say argon is the noble gas that comes before it, and then we'd say, oh, there's 4s2, 3d4. Let's do copper. Copper would be argon. So here's chromium, here's copper. 4s2, then 3d, how many? Count them. 9, right? Turns out these are not the correct configurations for chromium or for copper. The correct one is argon 4s1 3d5, and for copper it is argon 4s1 3d10. So what happened here? Well, for these, instead of the S being filled up with 2, it only gets 1 electron. And instead of the D having 4, it has 5 electrons. So it seems like the S's just get 1 and the rest of them go into the D's. If you add them together, you get 6, right, total, whether it's here or here. So it's not like we removed an electron or gained an electron or anything like that. They just, instead of going, the second S electron, instead of going into the S to fill it up to make it 2, it kind of went into the D, right, to make it 5. Same thing with this one. Instead of putting 2 in the S and 9 in the D's, we only put 1 in the S so we can put 10 in the D's. So why is that? Why does that happen? That we just, observe that that's what happens with electrons. Well, turns out if you have half filled, like exactly half filled, or completely filled sublevels, they are lower in energy and therefore they are more stable. And remember, nature prefers low energy and stable. So if you look at the copper family, if we only put 1 in the S, then that makes the D completely filled with 10, which is favorable. It is lower in energy, and that's pretty stable. And so this is the correct electron configuration for copper, not that one, because this one is higher in energy, not as stable. Same thing with this one here. The D sublevel takes up to 10, so half filled would be 5. And so if we can put 1 electron in each of these orbitals to make it half filled, that makes it more stable and lower in energy. So we notice that that happens with the copper family and with the chromium family, those two families. So silver does the same thing, or gold does the same thing, molybdenum does the same thing. So they only get 1 in their S's, and then either 5 for this family or 10 for this family in the D's. That way your D sublevel, which is really big, becomes more stable. There are many, many other exceptions, but those are the only ones that we're going to look at, is the whole chromium family and the whole copper family that do that. So based on this, these are the correct electron configurations. Based on that, how many valence electrons do these have? Well, the 4th energy level is your highest energy level, right? So they only have 1 valence electron.